WPR number 8. In the first question, we're asked to use the discriminant to determine all values of k that would result in the equation x squared minus kx plus 4 equals 0 having equal roots. If the discriminant is less than 0, then the result would be two imaginary roots. If the discriminant is greater than 0 but a perfect square, the result would be two real rational unequal roots. If the discriminant is greater than 0 and not a perfect square, the result would be two real irrational unequal roots. It's only when the discriminant is equal to 0 that you would have two equal roots. And so we need to set the discriminant equal to 0. Let's find our a, b, and c values. A is the coefficient of the x squared term, b is the coefficient of the x term, and c is the constant. The discriminant b squared minus 4ac must be equal to 0 for there to be equal roots. So I'll go ahead and fill in the b squared minus 4ac. So negative k is being squared minus 4 times 1 times 4, and that has to be equal to 0. When we square the negative k, we get positive k squared minus 16 equals 0. I could factor this into k plus 4, k minus 4. And the values of k that would result in two equal roots would be k equals negative 4 or k equals 4. In question 2, we're asked to evaluate f of negative 3. We establish f of negative 3 by replacing each of the x's in f of x with a negative 3. The result would be the square root of negative 9 plus the square root of negative 36. Now the square root of negative 9 would be 3i, and the square root of negative 36 would be 6i, and when I add those together, I would get 9i. We have a formula for the product of the sum of the roots. It's negative b divided by a. In this example, that would be negative 11 divided by 5. The formula for the product of the roots is c over a, which in this example would be negative 3 divided by 5. In this example, there are negative exponents, but the negative exponents are buried inside of the parentheses. So we have to eliminate the parentheses first. In other words, in the numerator, we have to raise each of the terms to the power of 1/2, and in the denominator, we have to raise each of the terms to the power of 3. This is called raising a power to a power, and it's accomplished by multiplying. For example, to raise x to the negative 2 to the power of 1/2, we're going to multiply the negative 2 by the negative 1/2, and so on. So in the numerator, we'll have x to the power of negative 1 and y to the power of 2. In the denominator, we will have x to the power of 9 and y to the power of negative 6. Now we can go ahead and move the terms that have negative exponents. So in the numerator, that x to the negative 1 will go into the denominator. The y squared will stay where it is. In the denominator, the x to the 9th will stay where it is, and the y to the negative 6 will move to the numerator. The result after multiplying is y to the 8th over x to the 10th. Whenever a problem says to factor completely, that means to factor out a GCF and then factor what remains again. And so in this example, we can factor out a t, and we'll be left with 3t squared plus 5t minus 12. And it's that 3t squared plus 5t minus 12 that can be factored. Again, using the AC method, 3 times 12 is 36, and I'm looking for numbers that multiply to be 36 that'll add up to 5. Now 1 and 36 don't work well because they add up to be 37 and they're different by 35. 2 and 18 don't work well because they add up to 20 and they're different by 16. 3 and 12 don't work because they add up to 15 and they're different by 9. But 4 and 9 work because they add up to 13, but they are different by 5. So I'm going to go ahead and replace this 5t with a positive 9t minus 4t. Now from the first two terms I can factor out a GCF of 3t, and I'll be left with t plus 3. The second set of terms begins with a negative, so I'll factor out a negative 4, and when I divide each of those terms by negative 4, I'll be left with t plus 3. That's a good sign. And now lastly on the inside, from each of these I can factor out a t plus 3. And when I factor a t plus 3 out of this, I'll be left with 3t. And when I factor a t plus 3 out of this, I'll be left with minus 4. So it looks like if it's factored completely, I'll be left with t times t plus 3 times 3t minus 4. Express the product as a trinomial. Well, remember that when you raise something to the power of 2, that means you're going to multiply it by itself. And so in this problem, I'm multiplying 2/3 x minus 1 by itself. That's a double distribution. So first I'll multiply the 2/3 x by the 2/3. I know when I multiply x by x, I'll get x squared, but 2/3 times 2/3, remember when you multiply fractions, you multiply the numerators together, and then you multiply the denominators together. So 2/3 x times 2/3 x will be 4/9 x squared. Now when I do the outside, I'll have 2/3 x times negative 1, and the inside will be 2/3 x times negative 1, and lastly, negative 1 times negative 1 is positive 1. I wish I could stop here, but I can't because the directions said to express the product as a trinomial, and I have 4 terms. I guess this would be a quadrinomial or a polynomial, but it doesn't have 3 terms. It's not a trinomial. But these are like terms, they can be combined. Negative 2/3 minus 2/3 would be negative 4/3. So negative 2/3 x minus 2/3 x would be negative 4/3 x. Now I have my 3 terms, I have my trinomial. None of them can be combined because they all have different exponents. I'm done.